Hello everyone again, and welcome to this particular video. And in here we're going to be focusing on a specific type of heck reaction where we're going to be dealing with creating products that involves a little bit of isomerization and how various segments of a specific compound might lead to the positioning of carbon hydrogen bonding relationship with palladium bonding with a carbon around a specific ring or a specific chain, and how that can lead to majority of the products actually having either an anti or a cis or syn formation. And in here we're going to be looking at alkene isomerization in heck reactions, and this here is going to be mainly focusing on a specific step that actually determines that particular isomerization, which is called a hydropalladation step, which is going to be something quite new, and we need to take note of some big ideas involving the hydropalladation reaction step, which is a form of a reverse reaction. So this occurs in a reversible beta hydride elimination, and this actually is a reductive elimination where there is a syn elimination involved between the carbon palladation bond with that of a carbon hydrogen bond, and this must be at eclipse with each other for this particular reaction to form a palladium hydrogen bond. So the next thing you need to consider here is that the alkane must move one position from one to the other, and finally the beta hydride elimination actually occur away from the allyl group, since there is only one carbon hydrogen bond that is syn to the carbon palladium bond. So you need to be aware of all these bond differentiation and similarities or relationships within a specific chain or ring that qualifies for hydropalladation to occur. Now, the big idea case involves this particular type of compound, and this is an organic halide, because we notice of course an iodine in there present, and this is going to be reacting with this particular form of a alkene, and this alkene is kind of a form of an, I would say, ketone alkene, and this actually is going to be done in the presence of palladium OAC, and this is going to be in the presence of this particular compound, and finally we have a base in that solvent, and that ligand in there is kind of used for ligand exchange, but that doesn't really matter at all. But in here, our first video here will be focusing on product A, and what is product A and when this reaction occurs, and next step will be, possibly the next video will be subjecting our product A to this particular compound naphthalene iodide, and this is going to be done in the presence of the catalyst and the specific base, and this will lead to product B. And you could imagine how all these various bulky group will be surrounding the catalyst, which is the complex, and how would this influence the product being formed, or determines mainly on the specific positioning of one bond to the other, mainly with the palladium carbon bond with that of a neighboring carbon hydrogen bond that must be syn to each other. Don't forget that. So in here we're going to focus on the big idea, which is in this video looking at the mechanism for step A, which involves product A being created. So looking at the mechanism here, we're going to start off with, of course, our catalyst, which is a transition metal catalyst, and this we know is having an electron number to be 14 electrons, which is palladium 0. So this has to go to palladium 2 through oxidative addition. since we know that this is a heck reaction, we're going to start off with the introduction of our organic halide, and this leads to the formation of two bonds that is surrounding palladium to create this complex. And this complex here, we notice, is going to be subjected to carbonmetallation, and this case here we're going to introduce our specific alkene, and this alkene here is going to position itself in a syn position. And before we consider that, we need to label numbers around this particular ring, because there will be something that will be revealing in terms of the movement of that particular pi bond. So in here, the syn position to the palladium and the pi actually leads both this particular migratory insertion of our group, which is an allele group, in the syn position, as well as that of our palladium. Therefore, in this particular case, we actually have our specific numbering that is taken care of, and we see that this particular ring here is actually syn to that of the complex, which is palladium. So the next step here is by beta hydride elimination, and what you notice here is that the hydrogen that is attached to the same carbon as the green compound is not syn to that of the palladium complex. So what we see here is that the other region, the next carbon, carbon 3, has a hydrogen that is syn compared to that of, well, related to the palladium complex. So therefore, in this case, if you're asked to pick which hydrogens is going to be involved in the beta hydride elimination, we will consider hydrogen B, not hydrogen A, because hydrogen B is actually syn to that of A. Therefore, in this case, we actually perform our form of partial beta hydride elimination, and you will see the reason why I call it partial. So what we see in here is that we have a partial double bond created that is interacting or attracted to the complex, which is palladium, and we have our palladium grabbing the hydrogen B in this process, and we still have our numbering system right there. So what we see is that our double bond is going from carbon 1 2 now to carbon 2 3, comparing our step 2, which involves the oxidative addition step, to the beta hydride elimination step, which is what we have right there. So something you need to be aware of. And now we have the next step where we have to decide on the hydrogens, and this leads us to the process called hydropalladation, where we have two sites that are opposite to each other, and we have hydrogens that may actually be involved in a process. So this, take note, must lead to the formation of a new sigma complex. So therefore, by moving away, don't forget that, from the aryl complex, which is the green compound, we actually perform our hydropalladation, where we have our complex moved one step over, and this leads us to the formation of our new sigma bond, which is the carbon palladium bond right there at carbon 3. So in here we have the next step. This, take note, is a reverse reaction, and this actually leads to the final step, which involves two carbon hydrogen that actually are syn to the carbon palladium bond. So we see that the two carbon hydrogen bonds are in carbon 2 and carbon 4, and you have to decide on which carbon's hydrogen bond will be sacrificed in here, because both carbon hydrogen bonds are syn to that of the carbon palladium bond. So this is where the next step involves predicting what the product will be. If we look at for picking either B or A, we actually notice that if we go for A is the right step, because A through the beta hydride elimination step, which is the second one, which is a reversible process. We actually won't consider carbon hydrogen that has the hydrogen B, because that will not lead to a more stable product. However, for carbon hydrogen A, that will lead to a more stable product. Therefore, the hydrogen A will be eliminated as a result, which will lead to the formation of an enol product, and this enol product is actually due to the creation of the double bond between 3 and 4. Therefore, we have an enol ester or ether, and enol ether is more stable alkene due to conjugation. Therefore, this is our product, and this product, taking note of it, is product A. So that's about it for this particular step in here, and if you want to continue from there through the process of reductive elimination, you introduce your base, which is the OAC. This actually comes in, picks up hydrogen A, which is the one that was involved in the beta hydride elimination part 2. This would then lead us to the formation of our cation in here, and so in here we're able to produce product A, which is this particular enol ether, and this actually leads to 78% yield in this particular process. So that is about it in here for this particular step A, which leads to the formation of product A. And on our next video, don't forget that we're going to look at step B, and little bit of hint here is that for step B, which leads to the formation of this particular product B with the presence of this naphthalene iodide, take note here that for this mechanism we will not need the hydropalladation. That is a little bit of the hint right there. So watch out for this step 2 video on our next video, and please, before you click off this video, please don't forget to subscribe and hit the like button, where you will be able to keep track on what is yet to come in the sequential videos to come. All the same, stay smart as always and believe in yourselves.